You know when you look at the periodic table and you see all those little boxes with numbers in them? Ever wonder what they're actually trying to tell you? Well, there's a whole story packed in there. And today, we're going to decode the two most important numbers for any element, piece by piece.
So, here's the game plan for today. First, we'll figure out what gives an atom its unique identity. Then, we're going to talk about the problem of trying to weigh something that's ridiculously small. After that, we'll look at the clever solution scientists came up with. Then, things get a little complicated with something called isotopes. And finally, we'll put it all together to see how we get those final numbers you see on the chart.
All right, first things first. What actually makes an element, well, an element? How does an atom of gold know it's gold and not, say, lead? It all comes down to what's inside its core. And it turns out one of the particles in there acts like a permanent, unchangeable fingerprint.
And that fingerprint is called the atomic number. Scientists usually just call it Z. And it's super simple. It's just the number of protons in the atom's nucleus. And here's the most important part. This number, and this number alone, defines what the element is. It is non-negotiable.
And this is what's so cool about it. If an atom has exactly one proton, it's hydrogen, period. No exceptions. If it has 6 protons, it's carbon. Got 17? You're looking at chlorine. No two elements can ever share an atomic number. It is the perfect ID system.
Okay, so protons lock in the identity. The count is fixed. But what about the other particle in the nucleus, the neutron? Well, that's where things get a little more flexible. The number of neutrons can actually change, and that creates different flavors of the same element. And trust me, that idea is going to be really important in a few minutes.
So we know how to identify an atom. That's solid. But how do we weigh it? I mean, your first thought might be, let's just use grams, right? But for the atomic world, that's kind of like trying to perform surgery with a shovel. The tool is just all wrong.
I mean, just look at this number. That's the mass of one single carbon atom measured in grams. That's a decimal point followed by 22 zeros and then 1993. It is a crazy, totally impractical number to write down every time you do a calculation.
Yeah, this really sums it up perfectly. The scale you're using is just completely out of sync with what you're trying to measure. So, what do you do when your unit of measurement is way too big for the job? Well, you invent a new one.
And the solution they came up with? It was absolutely brilliant. Instead of trying to find the absolute mass of every single atom in grams, they said, hey, why don't we just weigh them relative to each other? They basically created a whole new measuring system just for atoms.
And they called this new unit the Atomic Mass Unit, or AMU for short. Here's how it works. They took the most common form of carbon, called carbon-12, and just declared that it weighs exactly 12 AMU. That means 1 AMU is defined as exactly 1/12 of the mass of that specific carbon atom.
And that's really the key idea. You know how there's an official kilogram locked in a vault that everything else is measured against? Well, carbon-12 became that standard for the atomic world. Now, instead of those crazy numbers, scientists could just say an oxygen atom weighs about 16 AMU. So much easier.
Okay, but wait a second. This brings up a new question. If protons and neutrons each weigh roughly 1 AMU, then shouldn't the total mass of an atom be a nice, clean, whole number? So why, when you look at the periodic table, do you see numbers with decimals like 35.5 for chlorine?
Well, the answer is that when you grab a chunk of any element out in the real world, it's usually not made of just one type of atom. It's actually a mix of slightly different versions of that element, and these different versions are called isotopes.
So, what exactly is an isotope? It's really simple. All atoms of chlorine have to have 17 protons. Remember, that's its ID. But some of those chlorine atoms might have 18 neutrons, while others have 20. They're all still chlorine because the proton count is the same. They're just lighter and heavier versions of each other.
So if an element is actually a mixture of these different isotopes, how do we get that one single mass number for the periodic table? We can't just take a simple average. We have to do something called a weighted average, which takes into account how common each of these isotopes is out in nature.
And that final number is called the average atomic mass. But again, it's not a simple average, like adding two numbers and dividing by 2. It's a weighted average. Think of it this way. The isotopes that are more abundant get to have more of a say in what the final average turns out to be.
Let's go back to our buddy, chlorine.
If you scooped up a random sample of chlorine from anywhere on Earth, about 75% of it would be the lighter version, chlorine-35, and the other 25% would be the heavier one, chlorine-37. So right away, you can guess the average is going to be a lot closer to 35 than it is to 37, right?
And the math totally backs that up. It's actually pretty straightforward. You take the mass of the first isotope, 35, and multiply it by its percentage, which is 0.75. Then you do the exact same thing for the other one, 37 times 0.25. You add those two numbers together and boom, 35.5 AMU. And that's the exact number you see on the periodic table.
And what's great is that this method works for every single element. Let's take a look at gallium here. Yeah, the numbers are a lot more precise, but the logic is exactly the same. You just multiply the mass of each isotope by how common it is, add up the contributions, and you get your final average atomic mass. The process never changes.
So, when it all comes down to it, here's the big takeaway. The whole number, the atomic number, that's the element's identity. The number with the decimal, the average atomic mass, that tells you the average weight of its whole family of natural isotopes. Two simple-looking numbers, but they tell two very different stories. So now that you know how to read them, what other secrets do you think the periodic table might be hiding in plain sight?